Alright everyone, welcome back. In this video I want to talk about inductors. So the way inductors work has to do with magnetism, and it has to do with the right hand rule. But I don't want to get too far in the weeds of the physics of this. Hopefully you've taken physics and you understand the way inductors work in physics. Wherever you have a wire that's winding around, you'll generate a magnetic field which generates flux. But the way to think about this is as you have current as you have some electrons that try to move through this inductor, through this wire, what ends up happening is this generates a magnetic field. And the magnetic field you can, of course, imagine as going around like, something like this. Woo! Something like this. It generates an electric field or magnetic field that will initially oppose the motion of current, but then will eventually allow it to come through. So the inductor it blocks quick changes in current, but then eventually allows the current to go through. So one way we can imagine this is it goes up and then it finally does allow some current to flow. And likewise, what we see is at first you're going to have a voltage that appears across the inductor in the form of this stored sort of magnetic field, and then eventually it gets this energy that initially is stored gets used up. So what you end up seeing here, of course, is something like this. So as time progresses, you're allowing that current to pass through, and no longer are you impeding the flow of current. So think about this, right? If I have my battery, which is 9 volts, at first what's going to happen is this 9 volts is going to show up across the inductor. It's going to get stored along here, and as you see, there's going to be no current flowing. But over time, what's going to happen is this 9 volts that's stored is going to eventually get dissipated throughout the inductor, and what you end up seeing is you will eventually get current flowing. You will get current flowing through the wire. It just wants to block out these changes, these quick changes in current. And the analogy I want to give in terms of water is imagine you have a pump, and imagine you have a water wheel or something that is attached to a spinner. And what's going to happen is as you're pumping water through, you're going to have water coming out at a certain pressure, and it's going to hit one of these things. And eventually, what's going to happen at first is there's not going to be any flow here because the wheel hasn't started to move. It's basically impeding the flow of water. But as more and more water starts going through, as the pressure sort of builds up here in this wheel, eventually the wheel will start moving and you'll eventually have the flow that you want. It's going to take a lot of water pressure to get the thing started moving, or to change the actual velocity of the wheel. But once the wheel starts rolling, it just maybe would take only a negligible amount of pressure to sort of keep it rolling or keep the thing moving. You can, of course, in this analogy, you can imagine it has a lot of resistance to get started, but then as it's going, it's not too bad. So that's what we see here. And if you remember Eli the Iceman, with our capacitor, we had current leading voltage. In this particular case, L being the inductor, of course, L, and we use this sort of symbol with the squirrelies which is different than a resistor. Some people get these mixed up. The resistor is like straight lines. The inductor is like curved lines to represent the coils, because they actually have to be coils to have this sort of flux. In an inductor, what we see is voltage, E, which is voltage, coming first. You have some positive amount of voltage that's applied, and then current comes later. In other words, voltage leads current in an inductor, and usually we report these in farads, but the thing that we use, the variable that we use, is L. And we can relate these as integral and derivative expressions as we did before, like so. We basically say V of t is going to equal L, which is my inductance, times d dt of I of t. And likewise, if you look here at I of t as a function of time, and you just take the take the tangent line at any given point, what you see, of course, is at first no current is allowed, and then over time current goes through as some of that is dissipated. And similarly, what you see here is as these tangent lines, they pretty much flatten out, and you get what you see here on the left in terms of voltage. And likewise, using the fundamental theorem of calculus, we can use this to solve for our current. So I of t is going to equal 1 over L times the integral from minus infinity to time t of v of, let's once again introduce a dummy variable that will integrate out v of z dz, with once again the assumption that at minus infinity, or up until some finite amount of time, v of z was 0. So these are our expressions that we use to talk about inductors. Inductors kind of work the opposite of capacitors. If you remember, in capacitors, basically initially you have current and then the voltage comes later, which then causes your current to go to 0. With inductors, you have the opposite. You have voltage applied across the inductor, which stops current at first. They kind of happen simultaneously, and then eventually it lets current through, and you eventually have, I guess, what you would expect to see. You would have it behaving more like a wire over time as time goes on. So this is the way we relate inductors. This is how voltage and current. In our previous cases with resistors, these things didn't depend on time, but introducing inductors or capacitors actually introduces these phase shifts between voltage and current, which will come into play when we start talking about calculating power, because we need some sort of P equal IV, P equaling I times V. If these are functions of time, then power is going to be a function of time that's equal to the current as a function of time times the voltage as a function of time. So to get maximum power in your circuit, you need to have a phase alignment between your current and your voltage, which we will be talking about in the coming videos. So hopefully you found this video helpful. Once again, as an introduction to these, we'll talk about how to solve these, and then we'll very quickly say, yeah, solving these differential equations sucks. Maybe there's a better way we can do this. So hope you found this helpful, and I'll see you in the next video.